Welcome to another episode of 5G Tech Talk, your favorite podcast for everything you need to know about the next generation of wireless technology. Today, we are going to explore a critical feature of 5G network that's shaping the future of connectivity, and that is beamforming. We will break down this advanced technology and explore it various types, including analog beamforming and digital beamforming, as well as discuss antenna array techniques, focusing on differences between beamforming and beam steering. So, let's dive into it. What is beamforming? How exactly does beamforming work? And why is it so crucial in 5G? A great analogy to understand beamforming is imagine the differences between a spotlight and a floodlight. A spotlight directs light to a specific area in a room, like a torch, while a floodlight, similar to a 9-watt bulb in your room, spreads light across the entire room. With a spotlight, you can focus on a distant object like you do with a torch, while a floodlight allows you to see nearby objects all around you within the circumference of a room. Now let's keep this analogy in mind. We will discuss beamforming in detail. Let's start by exploring a few key benefits of beamforming. Beamforming improves both uplink and downlink link budget by increasing the antenna gate. With greater antenna gate, a focused beam can be created, resulting in better signal strength and coverage. Here you can relate beamforming with the torchlight, where multiple LEDs in a torch will converge to form a concentrated beam. This focused transmission enhances connection quality and minimizes interference from other signals, which is particularly beneficial for higher frequency bands like millimeter wave frequencies that are prone to air interference attenuations. By directing transmission in a specific direction, beamforming helps reduce interference between neighboring cells. The narrow beam minimizes the chances of interference across a wide range of angles, making spectrum usage more efficient and effective. Also, beamforming enables massive MIMO antenna to direct signal towards multiple users simultaneously. In essence, beamforming creates a direct connection between the base station and the user device, allowing faster and more efficient communication. It is especially beneficial in dense urban environments where multiple users are competing for bandwidth. Let's get a bit more technical to understand how does beamforming work. Beamforming works using an array of antennas with multiple antenna elements at the base station. Let's assume the size of an antenna array is a matrix of 8 cross 4, 8 rows and 4 columns. 8 cross 4, that is 32 cross polar pairs with vertical and horizontal polarization. Overall, that is 64 antenna elements, including vertical and horizontal polarization. The physical size of an antenna array depends upon the carrier frequency. This is because antenna arrays are generally designed using half-wave dipoles. That is, each antenna element's length is approximately half of the maximum wavelength. As discussed in episode 3 of spectrum, at 3 GHz, which is a decimeter wave, that is 10 centimeter, the half wave corresponds to 5 centimeter. So each antenna element size is 5 centimeter. On the other side, at 30 gigahertz, which is a centimeter wave, that is 1 centimeter, the half wavelength is only 5 millimeter. Therefore, as frequency increases, the size of each antenna element decreases. The similar size at higher frequency makes it feasible to include antenna array within the user equipment or mobile. As we know that without MIMO, all 64 antenna elements form a single beam. However, with 2x2 MIMO, two beams are generated each utilizing 32 antenna elements. One beam can use the plus 45-degree element, while the other uses the minus 45-degree element. And this plus 45, minus 45 degree, you can say it is the horizontal and vertical polarization angles. Similarly, in a 4x4 mouse configuration, 4 beams are generated each using 16 antenna elements. Now, let's understand the two types of beamforming: analog beamforming and digital beamforming. Two distinct approaches to controlling the direction and shape of radio signals in antenna arrays. Both are used to enhance the efficiency and capacity of communication system. In analog beamforming, the phase and amplitude of the signal are adjusted using phase shifter and analog circuitry before the signal is fed into the antenna element. In digital beamforming, the phase and amplitude of the signal are adjusted digitally at the baseband level for each antenna element. Please listen carefully that the digital domain, the pre-coding is applied and there is a requirement to have multiple parallel RF chains. Now, when the number of antenna elements is high, example, when implementing beamforming for the millimeter wave band, it becomes less practical to have an RF chain for each antenna element because each RF chain is expensive and consume a high quantity power. That's why digital beamforming is applicable in frequency range 1, that is 450 megahertz to 6 gigahertz only, while analog beamforming is applicable in frequency range 2, that is 24.25 gigahertz to 52.6 gigahertz. The primary benefit of analog beamforming is the reduced requirement for RF chains. Practical deployment are likely to support at least 2 RF chains and 2 beams to provide support for 2x2 MIMO. Digital beamforming enables the creation of multiple independent beams, allowing the system to serve multiple users in different directions simultaneously. While an analog beamforming form a single beam at a time, although multiple users can be served simultaneously, those users must be located in the same direction. On the other hand, if the user located in different direction, they can be served by the use of time multiplexing. That at one instant, the beam is pointing to user 1, on the other time instant, that beam is pointing to another user. Okay, so it is all about analog beamforming and digital beamforming. Now let's understand the two main type of antenna array techniques: 5G beamforming versus beam steering. Beamforming and beam steering are closely related concepts, but they have distinct role in improving the efficiency and performance of wireless communications, especially in 5G networks. Beamforming is a technique used to direct radio waves toward a specific receiver rather than broadcasting the signal in all directions. It uses multiple antennas to manipulate the phase and amplitude of signal in such a way that they reinforce the signal in a particular direction. In this, the antennas work together to create a focal beam aimed at a specific device, which increases the signal strength and reduces interference from other signals. The base station knows where the device is located and it can direct the beam towards that device for a more efficient connection. Now, beam steering is a dynamic form of beamforming. It not only directs the signal but also continuously adjusts the direction of the beam as the user moves. This ensures that the connection remains stable, uninterrupted, high quality communication even for moving devices like vehicles or mobile users. Imagine you are driving a self-driving car in a city. As your car moves through different intersections, beam steering ensures that the 5G signals stay focused on your vehicle, adjusting the signal direction in real time as the car changes location. This is critical for maintaining a reliable connection for applications like autonomous driving or real-time traffic management, where even small delay can be problematic. Both technologies, beamforming and beam steering, work together in 5G to enhance connectivity, improve signal quality, and manage the challenges of high frequency waves like millimeter waves, which are more easily blocked by obstacles. Let's see the real world 5G deployment to enhance user experience. For example, urban connectivity. In dense urban areas with high-rise building and large number of users, beamforming ensures that everyone gets a strong, reliable signal despite the challenges posed by physical obstacles and congestion. Smart cities. Beamforming is crucial in smart city environment where thousands of IoT devices, from traffic lights to surveillance cameras, need to communicate efficiently. Augmented and virtual reality. Beamforming helps reduce latency and increase bandwidth, which is critical for real-time application like augmented and virtual reality, where any delay can disrupt the user experience. Autonomous vehicle. As vehicles move through different environments, beamforming ensures they maintain a fast and reliable connection to communicate with traffic infrastructure, other vehicles, and navigation system. By now, we understood why does beamforming matters for 5G. As we discussed, beamforming is critical for 5G network for several reasons. Increasing strength. By focusing the signal on a specific user, beamforming significantly improves signal strength. This is especially important when using millimeter waves frequencies, which provide extremely high data rate but can be easily blocked by physical obstacles like walls, buildings, or even trees. Beamforming helps overcome these challenges by concentrating the signals where it is needed most. We saw it reduce interference. In traditional mobile network, signals are broadcast in all directions, which can lead to interference, especially in crowded area. Beamforming reduces interference by directing the signal to a specific user, minimizing the chance of it overlapping with other signals. Beamforming improves capacity and efficiency. 5G networks are designed to support a massive number of devices, from smartphones to IoT devices, all requiring fast, reliable connection. By focusing signal directly on each device. Beamforming helps optimize the use of available bandwidth, ensuring that multiple users can be served simultaneously without sacrificing performance. Beamforming enhances mobility. Another benefit of beamforming is that it works dynamically. As the user moves through an area, the beam can adjust and follow the user device, ensuring a strong connection wherever they go. This adaptability is key to maintain a seamless experience, especially for applications like autonomous vehicle or augmented reality, where connectivity needs to be stable and reliable on the move. That is for today's episode on beamforming. I hope you found the discussion insightful and that you now have a clear understanding of how this technology is transforming 5G networks. If you enjoyed this episode, don't forget to subscribe and leave a review on your favorite podcast platform. And stay tuned for more deep dives into 5G technology on 5G Tech Talk. Until next time, I am Modi Derani signing off, and keep your fingers on the pulse. Stay connected, stay ahead. Thank you.